So today we are going to start discussion on the MOSFET. Okay, like we started discussion on the BJT, we will discuss the basics of MOSFET, little bit about the physical operation of MOSFET, and in that context, I will show you some energy band diagrams of how the MOSFET works. And then after that, we'll go into MOSFET as a switch, like we did BJT as a switch. And following that, we'll go into MOSFET as an amplifier. Same process. So the word MOSFET, you may already be aware, means metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. So all this called metal. We don't use metal anymore, So we have replaced it with something else. Replaced with n-doped polysilicon. So n-doped polysilicon means we know crystalline silicon, which we use for all the devices, but polysilicon is amorphous silicon, which is not crystalline, which has many different structures in it. And if you go inside the polysilicon, look this way, that way, the other way, it will look different. So you can deposit polysilicon as a paste on top of the device, on top of your silicon substrate. Okay, so that is a different kind of material than crystalline silicon. So, and it's doped n-type. When you dope, you actually increase the conductivity, because if you dope n-type, you add a lot of electrons, and that will increase the conductivity of the polysilicon. So the n-doped polysilicon is like a metal, because its resistance is very low, but it is better than metal because it helps to turn on the MOSFET at a lower voltage. Okay? So it got the properties that you want in a metal, but it is better than metal, specifically as a gate of the MOSFET device. Okay? And this is a field effect transistor. That means you don't touch, there's no p-n junction. There are junctions. P-n junction is a very natural occurrence in semiconductor devices. Whenever you don't want a p-n junction, there will be a p-n junction, because whenever you have p-type and then you create an n-type on top of it, you will have a p-n junction. So p-n junction is always there, irrespective of you want it or you don't want it. So in a BJT, we want to use the p-n junction. We forward bias one junction, we reverse bias the other junction, and we have a transistor. But in MOSFET, it is field effect. We don't use a junction. But one principle remains the same, which is when you try to make a transistor work, you have to lower the energy barrier. Remember, you have to lower the energy barrier between the base and the emitter. You have to lower the barrier so that electrons can flow from the emitter over the base to the collector. So you have to lower the barrier. That principle doesn't change. Whenever you want to move carriers flow, there will be barriers to the carriers, and those barriers will have to be reduced. So in a PN junction, you reduce the barrier by forward biasing. You forward bias, the barrier gets reduced, and electrons can flow and go to the collector. In MOSFET, field effect transistor, we still have barriers. We don't use the forward biasing of junctions to reduce the barrier. We use what? Can you tell me? What do we use to reduce the barrier? What do we use to reduce the barrier? We have to reduce the barrier, isn't it? Otherwise the electrons will flow. And we don't use a forward bias junction to reduce the barrier. So how do you think we reduce the barrier?
Do we possibly use the magnetic field?
Huh?
Do we possibly use the magnetic field?
Electric field, exactly. Field effect. Same, electric magnetic field. So use a electric field rather in this case. So use the electric field to affect a reduction in the barrier so that carriers can flow. That's the basic difference in between a BJT and a field effect transistor. Okay, so another main difference between BJT and MOSFET is that BJT is a 3-terminal device, isn't it? You have collector, emitter, base. But MOSFET is a 4-terminal device. All FETs are 4-terminal device, okay? This is a 4-terminal device. Okay. Then the question comes, how does it look, For an NPN, you could straight away draw like this, a structure like this. And then you say this is your N, this is your P, this is your N. And you have NPN transistor, isn't it? Which is a BJT. BJT. In a MOSFET, what you do is slightly more. What you do is that you have a gate here. This is a gate. You apply a gate on top of the substrate here, and then you have a source here. You have a drain here, okay, and then this P can extend all the way underneath. See, you can have the P all the way. So you can remove this, have all of this P, and then you make a connection here to the P. We call it body. So this is the structure that you can go into starting from a BJT. This is a MOSFET. Okay. So you have an NPN, then you put a capacitor on top of it, a gate here, and then your P, allow the P to continue across in all over the place beyond these two regions. So then this is your MOSFET. Okay. So you have 1 terminal, 2 terminal, 3 terminal, 4 terminal. 4 terminals. Okay. So this is just an introduction to how you could go into a MOSFET starting from a BJT. Now many other questions will arise. What is this material? What is this material? What is this here? And this region is called what? This region is called a channel. This is a channel. So you have a source, basically means a source of carriers. Okay? Source of carriers. Drain, where the carriers go into, drain into. It's like our normal water drain, You have something here going through the drain to the other side. So this is your drain. Drain, this is your source. This is your gate. And this is your channel. So in this case, this channel can be consisting of holes, or the channels can be consisting of electrons. So it can be a p-type channel. You can have a p-type channel, or n-type channel. That means a channel consisting of holes, or a channel consisting of electrons. So in this case, what do you think the channel is? This is p-type region. This is p-type body. Okay, this is the body. So this channel here between the source and the drain should be what type here, you think? This channel should be what type? Should it be n-type or p-type here? The body is p-type. The channel should be p-type or n-type?
P-type?
If p-type, there won't be any current flow, because the source of carriers is electrons, the drain is electrons. So you basically want electrons to flow along the channel into the drain.
Okay. So it's n-type.
So it's n-type, exactly. So here you want an n-type channel. N-type channel. So you distinguish a MOSFET between the type of channel, N-channel MOSFET or P-channel MOSFET. Okay? So if you are thinking about a P-channel MOSFET, then you can draw another diagram here, which we won't study in detail the P-channel MOSFET. We'll be mostly studying the N-channel MOSFET. So the P-channel MOSFET, you can all simply draw the similar thing here, where you have a N-type body. So you have an N-type body, and then this N regions will have P regions here, one P here, one P here. You understand P and N, means or P-type doped, N-type doped, okay? And then on top of it, you will have a gate. Then you will have your source here, and you will have a drain here. And then you will have a channel here. Okay, and this channel will be what type?
P-type?
P-type channel. Okay, so this will be a P-type channel. Okay, so this actually, you can create, the whole thing can be created on original substrate, which is the original substrate will be P-type. And then this N-type body you can create by making an N-well. So you have the original body, the substrate of the silicon wafer is P-type. Then you make an N-well here, dig out an N-well, and then inside the N-well you make two P diffusions, create two P-type islands. Then that will be the source and drain of this. Okay. And then here for N-well you have to make a well connection. This is again with the body. Okay. So one small thing which I want to add, which needs a lot of explanation, and I'm not going to spend a lot of time to explain, is that whenever you do this, you have to make an N plus diffusion here, N plus. And you have to make another N plus here. You have to make a P plus here. You have to make a P plus here. I'll tell you simply why. It's because if you don't do that, you will make Schottky diodes. You know Schottky diodes? S-C-H-O-T-T-K-Y, Schottky diodes. Schottky diode is a diode due to the connection of a metal with a semiconductor. If you connect metal with semiconductor, it still can make a diode. We know that you can make a diode using a P diffusion, P-type and N-type. You can also make a diode with a metal. If you take aluminum, touch N-type material, it will make a diode. And for that diode, the turn-on voltage is around 0.35 volts instead of 0.7. So it's very dangerous to just take a metal and touch a semiconductor and think you have a perfect contact. No. What you want is a contact where it is not rectifying. That means the current can go either way without any resistance. That's the kind of contact you want. So you have no intention to make a diode here. What your intention is to make the current flow this way or the other way. So for that you have to make a N plus highly doped N diffusion here, so that it makes a contact which is called ohmic contact. This is called a ohmic. Okay. So everywhere you have to do it to make a ohmic contact. That means this contact, the ohmic contact and the Schottky contact, difference is the ohmic contact conducts current equally in both directions, irrespective of how you apply the voltage, whereas the Schottky contact will rectify. That means one direction it will give current, the other direction it will obstruct the current. So it's a diode. So we don't want a diode here. So in this operation of this, we don't like any diode here. We don't want any diode here. We don't want any diode here. Also, this junction between N and P, there is a diode, isn't it? There is a PN junction here. There is a PN junction here. We don't want them. We want to reverse bias them so that they don't obstruct the operation of a MOSFET. So here we are just trying to operate the MOSFET, not the BJT. So all the PN junctions must be silenced, quieten them down, so that they don't become active, like a volcanoes underneath us, deactivate them. So how to do that? You have to reverse bias the junction. And so here what you do is that wherever you have this, you have to connect, this is N-type, you have to connect the most negative voltage here, most positive voltage, connect most positive voltage. That means if you have 5 volts in your system, whatever you're building, say you have 5 volts, you must connect 5 volts here. If you connect 5 volts here, all other voltages will be lower than that. So that means this PN junction cannot turn on, this PN junction cannot turn on. And wherever the body here, this is the P-type body here, the substrate. This is the substrate, so you will have substrate contact here. This is P plus, okay. This is the substrate. Connect to the most negative voltage you have. So if you have a system, your maximum voltage could be 5 volts, your minimum voltage could be 0 volts, then you connect 0 volts here. If you connect 0 volts here, you see P and this is N, it will not be turned on because this is at the lowest potential. So none of the junctions can actually turn on. Okay. Any questions? Is everything clear?
So for both examples, the body has to be connected to the most positive voltage.
The body, no, not the body. Given what type, P-type body, this will be connected to the most negative. This is P-type. Okay. So the P-type body for the NMOS is the same as the substrate for the PMOS. Okay. The same P-type, which is the substrate, is the body for this one. So only thing is that I should not show it like a box, I should show it like this, then it will be clear. See? So this is your substrate. Okay, so all of this is substrate. Okay? You can collect this all together. So now you see, all of this is substrate. All of this is substrate. One continuous substrate. On this you have your N MOSFET here, and here you have your P MOSFET here. It's all continuously. So this all is P-type. P-type substrate is the body of the NMOS, and for the PMOS you have to actually diffuse a well, N well, that will form the body of the PMOS. This is not the body of the PMOS. This is the body of the NMOS.
Why don't you need another like substrate kind of thing within the N-type body there?
Here?
Another N-type body, because you've got the body, the positive going in, but you don't have a negative going out of that.
No, here it is the connect to 0 volts here.
Yeah, but isn't that connected from that one?
It's the same. This is this thing continuously. So you can connect, if you connect this to 0 volts, then this is also 0 volts. Then you may want to connect another 0 volts here, or you can leave it alone because all of this is the same thing.
Yeah.
So you have 0 volts here, 0 volts here, 0 volts here, 0 volts here, everywhere 0 volts.
But you don't need something that goes through the N-type body, do you? You don't need like another
Here?
wire coming out. Yeah, you don't need another wire coming out the.
No, I have one here for the body connecting to the most positive supply.
Yeah. And that'll just go to the substrate there.
No, this is separate. This is separate, and this is separate.
Yeah. So why doesn't that need a wire coming out of the N-type
Which one?
side?
Come
The-
show me.
The N-type body. Because you've got this and it goes through here.
Yeah.
Why don't you need something going from this one to like a wire coming out of here?
You don't need it. No, you can put it. You know, you can put it like this here, and plus you have to make another division, connect to wire. And this is the same thing. You know, this is you can put 5 volts here. That's the same thing.
Yeah. Okay.
You can do it if you need it. If it's too large, then maybe you want to do it. You know,
Okay. Yeah.
it's no problem. You can do it. You can add another one here if you want. Another one here if you want.
Yeah.
You can add both substrate, one here, one over there.
Okay, so it doesn't really matter. Okay.
Depends on your design. When you're doing detailed design, then there are a lot of things you will have to do which is beyond the scope of this second year paper,
Yep.
second year subject. Course. We don't call papers anymore. You know that? We call them course. This is the analog electronic course. You know. It's not a paper anymore. Is it clear so far? The basic construction, basic operation. Is it clear? Anybody a question? Rangi? Anybody over there? Are you all perfectly happy with this discussion so far?
We'll use this to construct CMOS. This is the way we start.
Yeah, this is where we start to construct CMOS. Yeah. Anybody else? Yashka? No question? Okay, so now that you know the basic construction of a CMOS, which consists of a NMOS and a PMOS, now we want to talk about how you turn it on, isn't it? Every time you talk about a BJT, how you turn it on, you know. What do you mean by turning on? By turning on, you mean creating the channel, you know, this channel. So initially this channel is not existed, you know. Initially here, you have this P-type body, everywhere is P-type. These are all P-type here. So you want to make a channel which is N-type. How do you make it? By field effect. How do you apply the field? Through the what? Through the gate, exactly. Through the gate. So you have to apply. So you want to make an N channel here. What voltage you have to apply here? Positive or negative?
Positive?
Positive, exactly. You have to apply positive voltage. What will happen is that the positive voltage, now if I go more into the details, you see I'm going more into details now. What will happen is that if you look here, look under the channel, what do you have in the channel? You have P-type. That means you have acceptor ions and holes. Correct? This is what you have in the P-type material, acceptor ions and holes. So if you apply positive voltage here, positive voltage, all the holes will be driven out, isn't it? Holes will be driven out, but can you drive out these negative ions? They are fixed in the lattice, so they can't drive them out. So you apply positive voltage, this will go away, this will go away. and if you apply large enough positive voltage, you will attract electrons principally from the source here. Electrons will come here. So you will have a thin layer of electrons here. And then you will have a channel. So if you apply a voltage between the gate and source, VGS, between the gate and source you apply a voltage greater than VTH, this is NMOS, VTHN, then NMOS will turn on. Okay. So you must apply a voltage greater than a threshold voltage, VTHN, which is called a threshold voltage. So like BJT, you have a turn-on voltage, but this turn-on voltage is quite different from the BJT. Okay. And what is here? What is here? We didn't talk about that. We talk about this. We talk about this. But what is here?
Electric field.
It is the gate. Between the gate and the substrate. This substrate between the gate and the substrate. Substrate. Between the gate and the substrate, what is this thing here? What is here? Like what is here? Is this vacant? It is empty? Is it floating? What?
Is it like a battery in a terminal?
It is. It looks like a battery, but it's not really a battery.
It's a capacitor, so it needs like
Capacitor. Okay, this is a capacitor. So between here and here is a capacitance. So these are the two plates of a capacitance. Two plates. So when you have a capacitor, two plates. What do you have between the two plates? What is there between the two plates of a capacitor? Huh? Electric field is if you apply voltage, but I'm talking about the material between the two plates. Dielectric, exactly, dielectric. So, what is the dielectric here, you think? How to make a dielectric? Because this is all silicon. This is all silicon. Silicon. What is the easiest dielectric that you grow on? You can grow on silicon. What is the easiest? Huh? No, polysilicon is just polysilicon is the gate. This is the gate. The gate is polysilicon. So what is the easiest way to create a dielectric on top of to grow a dielectric on silicon? What is the easiest way to grow a dielectric? So you have silicon. Just grow a dielectric, then you will have your dielectric. What is that? How can you do it? Any idea? You can also use a dielectric as a paste. You can take some paste and put it as dielectric, which may not work as well as being able to naturally, grow a dielectric on the silicon. What do you think can be grown on silicon to be used as a dielectric without depositing a paste on top of it? What do you think? Think chemistry. Chemistry. Anybody?
silicon.
Silicon, yeah. How can you grow a dielectric on silicon?
Maybe silicon oxide.
Excellent. What was the name?
Marco.
Marco, yeah. It's brilliant. Marco got the brilliant idea. So, oxide. SiO2. You take silicon, you oxidize, you get silicon dioxide. Okay? So this is all SiO2, silicon dioxide. Okay. See, this is where Marco got the clue. Did you, or you probably thought yourself? Oxide, is it? Metal, polysilicon, semiconductor. You see, this is your metal. Your metal you replace with polysilicon. Then you have oxide, and this is semiconductor, just pure silicon, N-type or P-type. So that's how you got your metal oxide semiconductor. Okay. The clue is always there somewhere. See, you don't have to look too far. So now you know in material, you know that you have to apply a certain voltage between the gate and the source, which must be greater than the threshold voltage to turn it on. And in this case, it must be positive because you are trying to make a channel of electrons. Okay. So if you make the channel of electrons, will the current flow from the source to drain? You make the channel. Will the current flow? Will the current flow immediately? You make the channel. Will the current flow now?
No.
No?
Apply a source.
Apply?
A source. Like a voltage source. I think.
Exactly. So just creation of the channel is good. That means you have a path for electrons to flow from the source to drain. Then you have to apply voltage VDS. You apply VDS. Apply VDS to flow current. You apply VDS to flow current. So how much VDS apply, what will happen, that is another story. Okay. So now we go to P MOSFET. Okay. So here to turn on the MOSFET, initially you have N-type. So you want to try to make a channel of P-type. Okay. So what will be the situation here? So initially there is no channel. There is no channel. You want to make a P-type channel. And this is the N-type body. N-type body, what do you have? Electrons and, remember, go back to your doping. In N-type material, you have electrons and what? What is the kind of ion you have in N-type? Ions are what type? And carriers are what type? Carriers are electrons, which is negative, and then you have ions. What is the charge of the ions?
Positive.
Positive. Of what? Ions of what?
Phosphorus.
Yeah, a donor ion. Donor ion. Okay. So you will have ions here and electrons. So you can again draw like this. You know, you have ions. And you have electrons. Corresponding to each of these ions, you have one electron. But you don't want a channel of electrons here. What you want is a channel of holes. Okay. So to create a channel of holes, you have to apply a voltage, positive or negative?
Negative.
Negative, isn't it? Negative. So you have to apply a voltage which is negative here. That negative voltage will drive away these electrons from here and attract holes from the body, so you'll have holes here. Instead of electrons, at the edge of the substrate, you'll have holes. So now you'll have a P-type channel. So this will give you a P-type channel. So in this case, the VGS, okay, in this case, VGS must be what? Absolute value of the VGS, because negative must be greater than absolute value of VTH of P, threshold voltage of P must. Because why? Because VGS has to be negative, VTHP is negative, so it must be a negative voltage of value larger than a, so actually if you don't put the absolute value, then VGS will be less than VTH, isn't it? To turn it on, because it has to be a larger negative value than the threshold voltage, which is negative. So in order to avoid confusion, I always use this, that the absolute value of the gate to source voltage must be greater than the absolute value of the threshold voltage for the PMOS. To turn it on. Okay. And then you have to apply a voltage into the source and drain. So here you have to apply a voltage for electrons to flow this way, isn't it? Source to drain, electrons flow this way. So will this voltage be higher than this voltage, or this will be higher than this voltage? For carriers, so when you say source, means source of the carriers, from where the carriers will flow. So in this case, the carriers are electrons which will flow to the drain. In this case, the carriers are holes which will flow from the source to the drain. So in this case, is this voltage greater or is this voltage greater to cause the carriers to flow from the source to the drain? Is this voltage greater or is this voltage greater? Which voltage must be greater, drain or source?
Source voltage? Source.
For the carriers to flow, carriers are electrons. Electrons must flow from here to here. So this voltage should be higher or this voltage?
Voltage is drain.
Which voltage should be higher? You read it from there, right?
Right.
Yeah. Any other answers? Which voltage should be larger? Anybody is from there? Has to flow from the source to the drain. Electrons. So electrons must flow from the source to the drain. So which voltage must be larger? Simple question. If you have one electron here, okay, and it is sitting at this point 1, and you want to take it to the point 2, then this voltage has to be larger or this voltage has to be larger? We have one electron sitting here, and you want to drive him to point 2. You want to send him here. So is V1 greater than V2 or V2 greater than V1? From here, electron has to be sent here. So you want to apply a larger voltage here or here to drive it here? What does larger voltage mean? Larger voltage means larger positive voltage, isn't it? So you want to apply the larger positive voltage here or here, so that it will be attracted which this way. Where? Drain, isn't it? Here too. It's a simple question. So you have to be, so VD must be greater than VS for carrier to flow this way. So if the carriers, electrons flow this way, which way is the current flowing? The electrons are flowing this way, which way is the current flowing? Somebody there looking at mobile phone, Why are you looking at mobile phone, You can't use mobile phone here, never. Who else is using mobile phone? Who else is using mobile phone? You can't use mobile phone in the class. So you tell me, if you have over the other side, MOSFET, you want to make the holes go from the source to the drain, which voltage has to be larger for holes to go from the source to the drain? Voltage in the source will be larger or voltage in the drain?
Electrons are negatively charged. Yes,
Next. Carriers
Very specific. I wish I'd known that we were designed on circuits.
You're an engineer. You have to do that in
Man, I wish I knew exactly what to do within the circuit.
exactly the transistor. And if there's a wire, switch, which is what it's like.
So you make sure, so now you give me the diagram. You must realize, what you give is the wrong answer. So of course, if you give the wrong answer, the next one is the correct answer. So, but you must know why you So you have to apply a higher voltage at the source and a negative voltage compared to the source and the drain, so that the carriers will flow. The holes will flow. Holes are carrying positive charge, so they are attracted by a lower voltage. So you have to apply lower voltage here and high voltage here, so that the holes will flow this way. Okay. So that's the basic way of operation for NMOS and PMOS. So here, the source and drain. Is the source and drain fixed by construction? When you like in a BJT, you construct the emitter, you construct the collector, and the collector emitter cannot be changed, isn't it? In a BJT, can you change the collector emitter? It will reduce your beta, isn't it? So it's not of any good trying to use the collector as the emitter or the emitter as the collector. Can you interchange source and drain here? Does it matter if you call the source as drain and drain as source? Just interchange them by reversing the polarity of your drain to source voltage. Does it matter? No, exactly. So in MOS, it is a bilateral device where you can change the source and a drain. Nothing changes. So that way you can see that the BJT compared to the BJT, the MOS is a better switch. The MOS will make a better switch because the source and drain doesn't matter, You can put this either way, doesn't really matter. Whereas the BJT does matter, how you connect. Okay. So, have I covered all of the fundamentals before I go into the diagram showing how it actually works? Okay, so threshold voltage. Another thing is the threshold voltage. This voltage, threshold voltage, okay, VTHN. VTHN is actually given by expression. Okay, it is given by expression which is equal to VTHO plus gamma into square root of VSB plus phi f FP twice phi f. It's a bit complicated, okay? But you don't have to deal with this much here. I'm just showing you, You don't have to ask to calculate this value or anything. Twice phi f minus square root of twice phi f. If put a P, you can put a P here. Now this looks a bit complicated, but it is, yes?
What's the symbol in front of the brackets, please?
Yeah, that's a good question, VTHO, this is gamma. The Greek alphabet gamma. So this VSB, you see the VSB is the voltage between the source and body. So you see here source here and your body here. So between the source and body there may or may not be a voltage. So the threshold voltage, the voltage you require to turn on the transistor, okay, will consist of this thing. Where you have contribution of VTHO, that means this is the threshold voltage, basic threshold voltage. If VSB, you see VSB is 0, how much is this part? If VSB equal to 0, how much is this part?
0.
0, isn't it? If VSB is 0, this part is 0. And that case, your VTH in is just VTH NO. NO. That means the threshold voltage of NMOS at 0 voltage between the source and the body. So if there is no voltage between the source and the body, if they shorted, if you short them together, then there is no voltage between the source and the body. In that case, this will go away. This will go away, and your threshold voltage will be just the threshold voltage VTHNO. That means 0 voltage between the source and the body. You understand? Can you see from there? You hope so, or you?
Yes, I'm just curious how many equals 0 these things.
If VSB equals 0, okay, if VSB equals 0, there's a negative sign here, you see? Negative sign here.
Yeah.
So if VSB equals 0, this is 0.
Yeah.
Then you have square root of twice phi f minus square root of twice phi f. Isn't that 0? Is it 0?
Yeah, I see now.
You can see now. So you might ask me the question, what is gamma? Gamma is a parameter from the construction. So we don't really not to know. Then phi fp is a potential, Fermi potential, which I will show you later on little bit, which is not very important to know also, just a physical parameter, okay? Fermi potential. This is called Fermi potential. I'll show you where it is when I draw some diagrams after this hour. Okay? But it is not very urgent for you or imperative for you to know exactly what this thing is. Because we will mostly using the value, we will mostly be asking the question, what is VTHN as a number? How much is 2, 3, 2.5, what? We will not be going into asking you, giving you value of gamma, VSB and all this. We will not do it in this paper, in this course. But the actual quantity, the VTHN can be broken down into these components. That's why I wrote here, show you that it is consisting of components. Similarly, VTHP is equal to a negative VTHPO, a negative sign here, and then gamma. This is gamma will be the N for the NMOS. There will be gamma P for the PMOS, and then you will have a square root again. Again, you have the square, the absolute value of VSB plus twice phi Fn, most likely in this case because NMOS, P-type. Sorry, because it's a PMOS, and then you have minus square root of twice phi Fn, like this. This P comes because of the P-type body here in the NMOS, and this N comes here because of the N-type body here for the PMOS. You see here this N-type, so that's why you have the Fermi potential for N-type. Okay, this is Fermi potential for P-type body, and this here Fermi potential for N-type body. Okay. So PMOS here you see N-type body. So for that the Fermi potential have got N. And for NMOS, you have a P-type body. P-type body. So that's why you have a P here. So this is gamma N, this is gamma P. Okay, so you have any questions, or we'll take a break now for 10 minutes?